Hi everyone, my name is Neha Kadam and this is the fourth lecture on printed circuit board fundamentals. Table of contents. So in this lecture we'll be covering printed circuit board requirements based on IPC standards, and under that we'll be covering these topics: lamination, weave exposure, haloing, measles, crazing, marking, and depenalization. So let's first study delamination, or we can, the other name to call it is blistering. So blistering or delamination occurs when the layers of your PCB-based materials experience a partial separation. This will cause gaps or bubbles that look like blisters. Delamination typically occurs in the production process when unwanted heat or humidity are present. So you can see the blisters and delamination. They look like this. And on a real PCB, they look something like this. So the cause of delamination or blisters are due to thermal shock or excessive thermal stress during soldering, or due to manual soldering, rework and repair process, moisture in the board, poor lamination process, etc. Now, the question is, how can we prevent delamination and blistering? So the prevention can be done by baking of board prior to thermal processing, or by keeping the PCB dry in storage area. So here you see some of the requirements given by IPC are mentioned over here. For example, uh, delamination or blistering shall not exceed 25% of the distance between the plated through hole or internal conductors, or reduce the space between the conductive patterns below the minimum electrical clearance. And they may propagate during assembly or operation. Separate criteria may need to be established. Measling is not the same as blisters or delamination. So this measling we will study in the coming slide, and then you will able to know the difference between these two. So now I'll move on to the next slide. So now here, this slide talks about the weave exposure and haloing. Now what is weave exposure? So weave exposure is basically a surface condition of base material in which the broken fibers of woven glass cloth are not completely covered by resin. Weave exposure is acceptable for class 1 and class 2, provided the conductor spacing is not below the minimum requirement. But here, for example, you can see the weave exposure here. And this is the PCB, and this portion shows the weave exposure, and on a real PCB it will look something like this. If we talk about the class 3, uh, this weave exposure is actually not acceptable. So if you're working on class 3 types of product, then you have to keep in mind that you don't have these weave exposure. Now let's see this. It shall not violate minimal electrical clearance, shall be no surface damage that cuts into the laminate fibers. Now let's see haloing. Haloing you can see in this picture, it's shown here. This is the haloing. It appears as a light ring in the base material around drill holes. In most of the cases, this is a mechanical cause damage to the woven material. Haloing is acceptable if there are no conductors close to the hole. The cause of this is due to mechanical fatigue or cracking during the drilling process or milling process. Now here it says it shall not affect the physical spacing from the edge to closest conductive pattern by more than 50% or more than 2.5 mm. So this requirement you have to keep in mind when designing the printed circuit board. Moving on to the next slide. So this slide talks about edge delamination, and for that the example is provided here. This is a PCB, and here you can see that this edge is delaminated, and the requirement for that is the spacing between the edge of the PCB and the conductor layer. It should be more than 2.5 mm, or we can say that it should be more than 50% 50% physical spacing from the edge to the closest conductive pattern by more than 50%. So this requirement should be met when designing the PCB. So you should keep in mind these minimum requirements are met. So this slide talks about land or conductor separation, and for that the examples are provided. So here you see there is a land separation here. The conductor is lifted up from the base of the PCB, and the same is here. We can see a separation here. So you should keep in mind that if you're working on a class 3 products, then the land area shall not be lifted when there is an unfilled via or via with no lead in the land. And there shall not be separation of circuit conductors from the base laminate by a length greater than one conductor width. So this is a very important point you should keep in mind when designing the printed circuit board and putting the components on your board. Now moving on to the next slide. So this slide talks about LAN conductor reduction in size and flexible circuitry delamination. Um so the LAN conductors, so it says the width shall not be reduced by more than 20% of for class 2 and class 3 and 30% for class 1. Uh, so so for if you're working on a class 1, then 30% reduction can be acceptable. Uh, and however, if you are working on a class 2 or class 3 products, then only 20% is acceptable. So this much reduced size are acceptable. Now next is flexible circuitry delamination. So flexible circuitry, I hope you know that there are two types of PCBs, rigid PCBs and the uh, flexible type PCBs. So here in the flexible circuitry delamination occurs in those types of PCBs which are flexible, and these delamination, as you know that these are the separation or the bubbles in the cover layer of the flexible circuitry, and it shall not cross more than 25% of the distance between adjacent conductive pattern. So the trimmed edge of the flexible circuitry shall be free from any kind of nicks, delamination, or tears. And this slide talks about the flexible circuitry damage. So the example is provided here, and this is a flexible printed circuit board. You can see here, this is a damaged uh, printed circuit board. These are not properly connected. So the functioning of this PCB will not be as per the requirement. So here, the nicks or hallowing along the rigid part of the edge of the rigid flex, which is this flexible printed circuitry, cutouts and unsupported holes shall not exceed more than 50% of the distance from the edge to the nearest conductor, or we can say 2.5 mm, whichever is less. You should keep in mind that mechanically created indentations caused by contact between the cover layer and molten solder are not rejectable. Care should be taken to avoid flexing conductors during inspection. Slide talks about the burns and non-soldered edge contacts. The example for burns could be incorrect placement of components, power failure, and overheating due to lack of space on the PCB. These are just few examples of things that can go wrong at the design and at the manufacturing stage, which can lead to burns. So we should keep in mind that burn shall not physically damage the surface of the assembly, and if that happens, that the PCB will be replaced for all three categories, class 1, class 2, and class 3. So here, non-soldered edge contacts. So for that, the example is given here, and you can see that how badly it has been soldered over here. It says, according to the IPC standard, that the contact area of the edge connector contact length shall be free of solder flux, including no clean process assemblies and other contaminants. So if this happens, then that will not be called a good design, and it may interfere into your proper functioning of the board. This slide talks about measles, and measles uh, is shown here in this PCB. The white spots you see are the measles. So basically, this measling is the presence of these white spots in the PCB due to in the wave interior. They signal a destruction of the elements in the board, but some small measling can be within your tolerance as long as they are not very frequent or you don't have measling that bridges conductors and soldering guys. Stress and production can also produce measling. And other causes are like measling occurs most often when there is not enough resin supplied during the lamination process of the PCB. Using proper production technique can help limit its development. However, some PCB measling will occur during the life of the board due to mechanical stress placed on the equipment. Now, here these are mentioned based on IPC standards. So, measles are not a defect. If measles areas exceeding 50% of the spacing between non-common conductors, measling is an internal condition which may not propagate under thermal stress, not shown to be a catalyst for CAF growth. So here CAF basically stands for conductive anodic filaments, and CF is metal filaments that can grow from copper via hole plating along the glass fibers embedded in the PCB materials, such as your FR4, which is a PCB material. These CAF can eventually short your via holes out, which is bad news for the reliability of products in the field and also for warranty costs and customer satisfaction. Now moving on to the next slide, here measles topic is continued. Additional information for determining laminate performance regarding CAF growth. You can refer to these IPC standards, IPC 9691 user guide and IPC TM 650. Additional information for measles condition, you can refer to this IPC book, IPC 6012. Now next comes the creasing. So creasing is basically a separation along the fiber bundles, uh, which is shown here. You can see this pattern here. This whole portion here, you see the pattern. This is called creasing. Most times it is caused by mechanical means such as bending of the board. Uh, Casing is much less controlled separation in the base material, forming interconnection between mesols and possibly adjacent conductive patterns. Therefore, the acceptance requirement for casing are set that in that way that the same it is same as the as you have seen in the delamination and blisters. So here some of the IPC standards are mentioned. For example, tracing shall not exceed 50% of the physical spacing between non-common conductors. Tracing at the edge of the board shall not reduce the minimum uh, defined distance between the board edge and the conductive pattern. If the minimum distance is not specified, not more than 50% or 2.5 mm, whichever is less. Now, next is the markings. Markings are basically the labels on your printed circuit boards, and marking should be done by appropriate non-conductive inks, labels, etched by etched character or any other method. And marking should be used to provide, that for the reference or for example in the logo, or if you want to put the serial number or part number, for that purpose it is used. And marking location should be such that to avoid any placing information under component, and should not be hidden in the hidden location. Uh, and marking should not be placed on surface covered with melting metals or opaque coating. And if you're using the etched marking, then you have to make sure that it is done carefully, because it may affect the electrical characteristics such as capacitance on the PCB. So here we can go through these points. Individual component marking reference designator. So it's the same thing. Components should be mounted in such a manner that markings are visible. Assembly identification shall remain legible after all process to which the item is subjected. Additional marking should not obscure the original supplier's marking. So all these points you have to keep in mind when putting the marking label. Now next is the depanelization. So here, this is the edge of the PCB has been shown here, and this image shows the nicks present uh, in the PCB due to depanelization. So depanelization shall not result in the following frayed edges or nicks that exceeds 50% of the distance from the board edge to the nearest conductor, or 2.5 mm, whichever is less. Loose burrs that affect form or fit or function. So that should be avoided. Now to see how, I'll show you an example of depanelization, and let's go to the next slide. So this video will show you depaneling of the PCB. So this is it for the lecture. Thank you everyone for watching it.